A while back, I saw a pretty cool presentation on a thing called quantum levitation, where a superconductor is locked in a magnetic field and doesn't slide around like a normal magnet. I had to do a fair bit of digging on the internet before I found a straightforward answer as to why this phenomenon occurs. So I decided to put together this short 3-minute video explaining the basics of quantum levitation. Quantum levitation involves two things: a magnet and a superconductor, usually with an insulating pack of liquid nitrogen to keep the superconductor cold. A superconductor is a material that transfers energy with near to perfect efficiency. A normal power cord conducts electricity through the copper wire inside. But if you've ever had a cord plugged in for a long time, drawing a lot of energy, when you touch it, you realize it gets warm. This is because some of it is turned into heat because of resistance, friction in the wire. This property of electrical resistance is what makes you able to cook on your electric stove, run a space heater, and even create light. A superconductor, on the other hand, loses no energy. Electric and magnetic waves pass freely through a superconductor. So what happens? As fast as the charge contacts the material, the charge also wants to exit the material. You can think of it like rolling a ball up an incline, or like swimming against a stream. The charge moves in the direction of the material, but the material is at the same time expelling it as quickly as possible. This is called the Meissner effect, the expulsion of a magnetic field from the interior of a material that is in the process of becoming a superconductor. These two forces cancel each other out. The magnetic field slips around the superconductor instead of going through it. This creates a pocket in the magnetic field. Now, if there weren't any other forces acting on the superconductor, it would stay where it's at. But slight variations in gravity, air movement, and other forces cause the superconductor to slip and slide around. So how does the superconductor in the video simply stay in place? Skyhook. Just kidding. Engineer joke. Quantum locking is the answer. The further a magnetic field has to penetrate a superconductor, the more it is repelled. In most cases, the magnetic field is repelled completely because it lacks the energy to overcome the Meissner effect. But in these particular demonstrations, the superconductor is extremely thin, in the realm of microns, which means the magnetic field is able to overcome the Meissner effect. But this doesn't happen everywhere on the superconductor. Unless the superconductor is perfectly flat and smooth, there are certain areas of the material that are thicker and thinner. Little variations in the superconductor's surface, impurities, act as weak points, where the magnetic field can get through easier. These weak points cause the magnetic field to bunch up, like water going through a strainer as it passes through the superconductor. These are called flux tubes, columns of magnetic energy that pin the superconductor in place within the magnetic field. Any motion of the superconductor requires energy in order to realign the flux tubes, so the superconductor naturally wants to stay where it is at. Quantum levitation.